Limits graphically. So you see our fancy definition here. So the limit as x approaches a, and that negative in the exponent spot means from the left. So our x value is approaching some number on the left side, and then our function is approaching some y value, capital L. And then also, if that same limit is approaching on the right side of that x value, it's equal to the same thing, then the limit, air quote, at that particular x value is the same. So you can read the sentences there. So let's walk through a particular graph. Now this relates to some algebra when you did domain and range. Not 100%, but it's very similar. You might recognize a graph like this. So what we're going to do is pick some specific values of x. We're going to look at what the graph is doing from the left side and what the graph is doing from the right side, and then compare those values and see what conclusions we can get. So our first one, we're going to deal with the x value of 3. That's the part A. So from the left, or negative 3, so from the left of negative 3, we can see that graph is approaching the y value of 2. And it doesn't matter, there's an open dot there, not for our purposes. The graph from the right, so x going to negative 3 from the right, is a different y value. As that graph gets close to negative 3, it's getting close to the y value of 0. And our definition at the top says if those are not the same, then the limit doesn't exist. So one side is going to 2, one side is going to 0. They're not the same. It doesn't exist. The last part is just evaluating the function. F, what is the y value when the x value is negative 3? That's the solid dot. So that solid dot matters. So that answer is 0. Part B, we're going to look at positive 1. Same thing. The left of positive 1, our y value is negative 8. The right of positive 1, there it is negative 5. And neither one of those are solid. Okay, I jumped the gun. So because those two are different, the limit doesn't exist there. And because they're both open dots, neither is solid, the function evaluated at that x value of 1 also does not exist. Part C, we're looking at positive 7. So positive 7 from the left, the graph shoots straight up. We assume it continues that way. From the right, it goes straight down. Those are still different. Positive infinity, negative infinity, the limit doesn't exist. And again, the function evaluated at 7 also does not exist. Let's look at the next example. A little bit different graph, similar. So we're looking at negative 7. So negative 7, the graph on the left is approaching the y value negative 6. The graph on the right is approaching the exact same y value, negative 6. So you can see for this part A, all of those are negative 6. The limit on the left, the limit on the right, and the limit are all the same. And because of the solid dot, the function when it's evaluated is also the same. And the next one is negative 4. So negative 4 on the left is approaching the open dot. Y value is 1. The graph on the right approaching the same open dot. Y value is 1. So the limit on the left is 1. The limit on the right is 1. So the limit is 1. But because it's an open dot, the function evaluated, there is no y value for us to evaluate. And then the part C, we're going to 4. So let's look at that on the graph. 4 on the left, the graph goes straight up. 4 on the right, the graph goes straight up, which is infinity. So the limit on the left, infinity, the limit on the right, infinity, the limit at 4, infinity, but there's not a numerical y value that corresponds with that x value of 4. And our last limit is a limit as the x is approaching infinity. This relates to the algebra concept of end behavior. You may recall that phrase. So as x gets larger and larger, it looks a little horizontal, and I'm going to assume that out at 10,000 or 100,000, it's not going to suddenly dip down. So we're assuming that that limit is going to be the y value of 1. So the limit as x is approaching infinity, the function is getting closer to the value of 1.